Hi everyone, my name is Chelsea Finn. I'm an assistant professor at Stanford, and today I'll be talking about extrapolation via adaptation, or essentially how continual learning will allow us to generalize more broadly. So, as a bit of background, I'm interested in the question of how we can develop broadly intelligent behavior through learning and interaction. And to do so, my research studies how robots can learn behavior in the real world, learning things like using a spatula to lift an object into a bowl, or how to play with children's toys, essentially inserting a block into a shape sorting cube, or figuring out how to place an object into a particular container by watching a human do so, as shown here. Here are just a few examples of the kinds of things that we try to study in the real world. And we like to study robotics because I think that robots can teach us things about intelligence. In particular, if we hope to build general purpose robots that are useful in real world environments, that I think they must be able to generalize to many different tasks, objects, terrains, etc. And I think this allows us to really study the kinds of problems that come up when you are faced with such challenging generalization problems. And so in this talk, my goal is to talk about basically exactly this, provide a perspective on generalization for reinforcement learning and robotics. And I think that many of these ideas will translate more broadly to other things like computer vision and machine learning. And of course, we'll be using a lot of machine learning to do this. So when thinking about generalization, I think we often find ourselves in a situation like this, where our train distribution is narrower than the kinds of situations we hope to be able to generalize to at test time. For example, maybe our train distribution is data collected in a lab environment or data collected in simulation. And the desired test distribution may be the real world, where you could encounter many different objects and many different environments. So how might we go about solving this problem? One very natural reaction to this problem is, well, I know how to use many different kinds of spatulas. I know how to generalize very broadly. Can I build in my knowledge into the algorithm in order to help it? For example, I know things about physics. Maybe I could program a simulator and use this to help generate data for the robot. Or can I program some notion of objects like spatulas into the robot? Or try to program in certain kinds of equivariances that we think exist about the environment, or build in certain kinds of neural architectures. But while this is a very natural reaction, I think it's also a bit problematic. And the first reason is that while we humans are good at generalizing, we don't actually know how we do it. And there's a whole field devoted to this in neuroscience and cognitive science. And even if you do think that you know how we generalize so broadly, we also don't know how to program it in. This is essentially kind of the approach of symbolic AI approaches that have been studied a great deal, but also have really been limited in their generalization and their abilities to actually tackle problems in the real world. So, of course, I'm not going to end this debate, but today I'd like to talk about if we can do better, if we can generalize beyond our training distribution without having to build in knowledge that we have ourselves. Even if you think that building in knowledge is the right approach, I think the things I'll be talking about today are also helpful to further expand generalization. Okay, so in particular, there's two things that I'll touch on today. The first one very briefly, and then I'll focus mostly on the second one. And the first idea is that, well, instead of trying to make your algorithm generalize more broadly, what if you simply try to train on equally broad data? Essentially, try to expand the training distribution. And to do this, we need to develop algorithms that can learn from scalable data sources. In computer vision, we've seen this success over and over again, right, by collecting large data sets and training deep networks on it. But in reinforcement learning and control, this has been a lot more challenging. And I'll talk about that in a minute. And the second idea is, if you are kind of already at the point where you can't expand your training distribution anymore, then figure out what assumptions will allow your algorithm to generalize further, and then use those assumptions in your algorithm. And the reason why this is important is that, or the reason why we can do this is that the IID assumption that we make in machine learning is very convenient, but it's also a very weak assumption, and there are many things about the world that we can probably, many other assumptions that we could probably leverage to do better. Okay, so let's first briefly talk about this first one. If you want your agent to generalize broadly, can you train it on equally broad data? So to look at this, I think we need to look at, in reinforcement learning and in robotics, what does our data look like? If we look at this, maybe like 3 to 4 years ago, some of the videos that I showed at the beginning, our data looked like a single object, a single task, and a single environment. So very narrow. And this is also representative of many of the previous reinforcement learning works as well. Now, if we look at 2 to 3 years ago, a little bit more recently, we see that there's been some progress. A lot of these works are training with many different objects, but a single task and a single environment. And then even more recently, we've seen works that start to broaden towards both many tasks and many objects, but also still in a single environment. And this is kind of the story in robotic reinforcement learning. I think in other studies of reinforcement learning, it's even worse, where we're training on like the half cheetah environment in OpenAI Gym. And in contrast to kind of the data that we collect in reinforcement learning, we learn from in reinforcement learning, in machine learning, it's quite different. If we look at ImageNet, for example, this was 10 plus years ago, and the data is significantly broader than anything we use in reinforcement learning, with many different objects, tasks, environments, viewpoints, lighting, and so forth. Essentially, by training on a much broader data distribution, we get much broader generalization. So this makes a lot of sense, and maybe I don't need to tell you this if you're already in computer vision and you already do this. But if we want to, essentially kind of what we've seen time and time again is that data scalability has a much more substantial effect on generalization compared to algorithm changes. And we've seen this with ImageNet, we've seen this with GPT-3 most recently, and so forth. And if we want to actually realize these gains of data scalability in the context of reinforcement learning and robotics, I think we need two things. We need large and diverse data sets that can be useful for reinforcement learning, and we need algorithms that can learn from these data sets. And my lab has been working on both of these directions and trying to make progress on them. The first direction in terms of leveraging large and diverse data sets, we've been starting to look at how we can actually share data across institutions for reinforcement learning. While this is, of course, not a novel concept in fields like computer vision, where you share data all the time, one of the challenges in robotics is you actually have different robots in different labs, and this means that you have to figure out how to transfer and generalize across robots. So we've been looking at that, and we've also been looking at how we can leverage videos of humans. There's all this rich data of humans on the internet doing various behaviors, and if we can start to figure out how to learn from videos of humans, then we may be able to tap into that rich and substantial data source. So here's two efforts that we've been looking at in terms of leveraging large data sets. We've also been working on building algorithms that can learn from these data sets. This includes things like batch offline reinforcement learning, which I think is very promising for being able to leverage large data sets. Essentially, these algorithms work by, instead of collecting data in the loop of reinforcement learning, which is very inefficient because you have to recollect your data every single time you run the algorithm, these algorithms learn from just a single batch of data akin to standard supervised learning and deep learning. So we have some recent work on both model-based and model-free variants of these algorithms. And then lastly, we've been looking at offline meta-reinforcement learning, where you have a batch of data for many different tasks that you want to be able to learn a prior from, such that you can quickly learn a new task. Okay, so I think that this will be critical for generalization in the context of reinforcement learning and robotics. Now, the next thing I'd like to talk about and really focus on in this talk is how we might generalize beyond the training distribution. And this is really important because there are going to be many situations where you can't actually cover the expanse of the things that you'll see at test time during training. And this is also where continual learning will play a big role, as we'll see in a minute. And when we think about these assumptions, we're going to, and what we want to generalize to, we're going to be thinking about this in the context of reinforcement learning in open world environments. Essentially, a robot that operates in a very large world such that it will constantly be seeing new parts of the world and new states. And in such open world environments, I think that there are two kinds of things that are important. There'll probably many others too, but there'll be two things that we focus on today. The first is being able to handle persistent and continuous shifts in the environment or in the problem. And this may include things like variation in lighting over night and day, variation in wind, variation in user preferences or mood, which may be changing periodically due to the day, due to the time of day, due to the day of the week, etc. So we'll first look at that, and then we'll look at being able to handle sharper changes in new situations, which may be caused by major events such as new demands that are being placed on the agent, or the agent entering a new part of the world, such as a new building. But first, let's talk about persistent continuous shifts. For both of these, we'll need to introduce additional assumptions in order to be able to handle these kinds of variation and extrapolation in the environment. And the goal will be to make these assumptions mild, yet also powerful. Okay, so let's start with persistent continuous shifts. And whenever thinking about a new problem, it's also worth considering what prior work exists. And the most probably well-known prior work for this sort of problem would be the framework of POMDPs, or partially observed Markov decision processes. And these allow you to, this kind of framework allows you to consider a wide range of problems that have various sources of partial observability that may vary across time. And it does cover the setting of handling persistent shift in the environment, but it may also be a bit too general in the sense that it's very difficult to develop algorithms that can tractably solve the general POMDP problem. Now, there's also a couple frameworks of problems that are a little bit more restrictive, that are a bit more tractable as well. These include Bayes adaptive MDPs and hidden parameter MDPs. And in these environments, there's essentially a hidden parameter that underlies the transitions and the rewards. And this hidden parameter is held constant within an episode and then resampled at the beginning of every episode. However, these hidden parameters are also stationary across episodes. So they're drawn from the same distribution at each episode, and this doesn't allow you to actually consider situations where these parameters are going to be shifting continuously. Okay, so motivated by these two kind of frameworks for problem settings, we're going to develop a new problem setting that's a bit in between the two. And we're going to call it dynamic parameter MDP. In particular, this we're going to have hidden parameters underlying the transition and the reward, just like the MDPs and hidden parameter MDPs. And these will be fixed within an episode. What's going to be different, though, is that the parameters are going to systematically shift across episodes. So the distribution of a parameter for one episode will be a function of the parameter of the previous episode. Okay, so how well do existing algorithms actually perform with such partially observed and kind of unobserved shifts in the environment? So we'll start with looking at just two very simple settings. One is a reaching task where the robot needs to reach a certain goal. The goal isn't observed to the agent and it shifts gradually over time. The second is a situation where there's this half cheetah agent. It needs to run forward at varying velocities with varying amounts of wind, where the wind and the goal velocity also both shift over time, and they can't be directly observed by the agent. They have to be inferred from the dynamics and the reward. And if we evaluate different algorithms on these two settings, we find that they perform very poorly. So SAC and PPO are two algorithms that, two kind of classic off-policy and on-policy algorithms for reinforcement learning, kind of state-of-the-art methods, and they both perform very poorly. And then finally, SLAC is a method that incorporates latent variables that can model partial observability, but isn't able to handle this sort of non-stationarity. The oracle in this case is something that directly gets to observe the non-stationarity in the environment. So we can provide that as a point of comparison to really see that these methods are performing very poorly. Okay, so how do we go about solving this problem? To do so, we're going to build upon the idea of casting reinforcement learning within the framework of probabilistic inference in graphical models. And in particular, we're going to introduce a dynamic latent parameter z into our graphical model that looks like this. So essentially now we're going to have this latent variable that affects the next state. And this latent variable will be constant within an episode and will shift according to some probability distribution. Now, a key assumption that we're making here that is going to allow us to do well in this setting is predictability. Essentially, the ability to predict what the next z prime is given our previous experience and our previous estimate of z. So how do we actually solve it given this graphical model? We can formulate the likelihood of this graphical model and solve for the variational lower bound. And this is formulated on the right. This equation might look complicated, but it's actually pretty simple. So this just corresponds to learning a model of the dynamics and the reward. This is used to form a representation. This term is modeling the latent variable shifts, essentially predicting exactly what the future will look like, what the future zi will look like as a function of the past. And then this term just corresponds to entropy regularized reinforcement learning. So essentially the first term we can use maximum likelihood, the second term we'll use the reparameterization trick to solve for, and the last term we'll use a standard reinforcement learning algorithm, in this case SAC. Okay, so we refer to this as lifelong latent actor critic in the sense that the latent variables are shifting over the lifetime of the agent. And if we look at the previous two settings that we looked at before, the two simple settings, we find that this algorithm is able to do substantially better than these previous algorithms by modeling the non-stationarity and anticipating how things will change. Further, we can look at two more challenging settings. This includes a Minotaur robot with a continuously varying mass of the robot, which could be representative of a payload, as well as this simple 2D object gathering task that has varying wind that affects the agent's dynamics, and it also has no resets in the world. So the agent, its entire lifetime, is navigating through this without ever having any sort of interventions from another human to reset it, for example. And it needs to collect, in this case, the red objects. And in both of these settings, again, we see that by modeling the variability in the environment and anticipating the changes, we're able to do significantly better than existing reinforcement learning algorithms. Okay. Great, so we can now learn amidst some amount of non-stationarity as long as that non-stationarity is predictable. Now, what about being able to handle sharp shifts and drastically new situations? We're going to consider a situation where we have one training environment or one training MDP, which we'll denote as mtrain, and a variety of new test environments. And we'll only be able to access mtrain at training time, and we'll have to be able to generalize to new environments. So for example, we'll first start in simulation and then we'll move to a more complex real-world vision-based task. But in this case, we'll start with the walker agent in simulation. We'll also consider other agents as well. The training environment will look like a standard environment where its goal is to walk to a certain position. And then the test environments will include various perturbations such as an obstacle, a force applied to the agent at a certain time step, and joints that are disabled, essentially motor failures for a certain part of the trajectory. Now, how might we go about kind of solving and being able to handle this, these shifts in the environment? One natural approach is to build upon the idea of robust control. And what this would involve is adversarially perturbing the agent during training in the hopes that it can learn how to be robust to those perturbations and then be able to handle various perturbations at test time. And this kind of approach can generate perturbed situations during training and lead to more robust behavior at test time, but it may sacrifice performance as a result if it's challenging to learn a single policy that's robust to all those changes. It requires an adversarial optimization, which may be a bit tricky, and it may not actually be feasible to apply certain kinds of perturbations in the real world without significant human intervention. So what we're going to do is we have this hypothesis, which is that reinforcement learning algorithms are brittle because they learn exactly one solution to the problem. And we have this simple idea that instead of learning a single solution, what if we learn and remember multiple solutions to mtrain. We think that if these solutions are sufficiently different, then at test time, you could adapt your solution set and pick the solution that still works on mtest, discarding the solutions that no longer work because of a change in the environment. So for example, consider this really toy illustrative setting where we may want to be the green agent, navigate towards the red circle. And so we learn multiple diverse solutions to this task. And now we see that if there is a change to the environment, such as an obstacle or something else, we see that in this case, two of the solutions are no longer viable, but one of the solutions is viable. And so if we can essentially identify that viable solution at test time, and there is still a viable solution, then we can be robust and extrapolate to that situation under a couple assumptions. So the first assumption is that we're going to assume that we can adapt with a modest amount of data on mtest. And we need to be able to do this if we can, to be able to figure out which solution is actually still viable in the test environment. And the second assumption is that the changes to the environment are local. And formally what we mean by this is that the optimal policy in mtest also does well in mtrain. And this suggests that there aren't kind of more global changes to the dynamics or to the reward that are completely different, such that none of the solutions in, none of the kind of diverse solutions used to solve mtrain are viable in the test MDP. And under these two assumptions, we should be able to achieve few-shot extrapolation or few-shot robustness to local changes in obstacles, terrains, friction, and so forth. Okay, so with this high-level D in mind, how do we actually go about learning multiple solutions? What we're going to do is we're going to learn a controllable space of diverse policies that achieve return that's within epsilon of optimal. Essentially, we want to learn many different policies that can do pretty well in our training environment. And to learn a controllable space of diverse policies, we're going to use latent variables and condition our policy on a latent variable z, where we want z to be able to control which solution you're actually using to accomplish the task. Lastly, to achieve a return of within epsilon of optimal, we use a constrained optimization. So what this will look like at train time is that we'll optimize this objective here, where the mutual information will correspond to kind of maximizing the entropy of the states, while also making the state predictable from the latent variable z. So this leads to controllable space of diverse policies. And this constrained optimization ensures that this policy is still doing well on the MDP. Then at test time, we'll then roll out k different policies each with different z's and return the policy for the best performing z. This will be a policy that essentially performs well on the test environment. We'll refer to this as structured maximum entropy reinforcement learning. And in our experiments, we tested robustness to a variety of different situations, the ones that I showed before. And we're going to compare SMIRL with prior approaches, including SAC, which maximizes entropy, but not in a way that's controllable, and may not actually optimize for diversity in the way that SMIRL does. We'll also compare to Diane, which SMIRL uses sort of as a subroutine, but Diane on itself, while it optimizes for diversity, it doesn't optimize for reward. And lastly, we'll also compare to robust adversarial reinforcement learning, which adversarially applies perturbations to the agent. When measuring a 5-shot generalization, we find that for varying degrees of environment change, SMIRL is able to generally achieve greater robustness than these prior approaches on a variety of situations, such as forces, obstacles, and motor failures. And to give some intuition for what's going on, if we look at kind of a policy learned by SAC at training time, this is what it might look like. And if we kind of run the best SAC policy at test time, in this case, we did condition on a latent variable z, but they aren't as diverse as before. We get something like this that isn't able to successfully complete the task with the obstacle. And now with SMIRL, it's able to learn different diverse policies that hop on one foot, the front foot, or the back foot, or sometimes even flip over to reach the goal position. And we see that the best policy at test time is able to actually solve this task effectively and move towards the goal position. Okay, so we looked at robustness in simulation what about in the real world? We're again going to look at the situation where we have a single training environment and multiple different test environments. And in this case, we're going to look at a grasping task where the robot has to figure out how to grasp any object from raw RGB images. And then in our test environments, we'll change the lighting to be substantially different. We will consider objects that are transparent, that are very difficult to see. We'll look at a checkerboard background, and we'll also change the morphology of the robot substantially. Now, the initial system is achieves a grasp success of 86%. This is using a state-of-the-art reinforcement learning algorithm, QT-opt. And when applying this policy to these new test environments, performance drops substantially to performance in the 30 to 50% range. Now, how do we actually go about solving this task? Again, we're going to make the assumption of the ability to adapt with a modest amount of data. Okay, but in this case, we're going to try to use a much simpler idea, which is just to try to fine-tune performance. We've seen that fine-tuning is very effective for computer vision, for natural language processing, but it hasn't yet been shown that fine-tuning is actually helpful for reinforcement learning. And this is actually not necessarily an obvious question, because reinforcement learning often tends to look very different from an optimization point of view than computer vision or natural language. So to do this, what we're going to do is we'll collect some base data. This will include 608,000 grasp attempts by the robot. We'll then use this to train our base Q function with the QT-opt algorithm. Then we'll take this Q function, we'll use this to generate data in the new environment. For example, in this case, when the robot gripper has been shifted by 10 centimeters. We'll collect 800 grasps, so this is around 1% of the initial dataset size, and then use this to fine-tune the Q function that was learned in the original environment. Then finally, we'll take the adapted Q function and deploy it in the real world in this new situation. What we see is that across a wide range of tasks that include varying visual differences and physical differences, performance is strong. We see strong improvements even after only 25 grasps. We also see substantial improvement gains after 400 grasps or 800 grasps, which corresponds to about an afternoon's worth of data. And lastly, we also find that ImageNet pre-training performs poorly in this domain, which isn't that unexpected, since being able to explore the environment is an important part of the fine-tuning process, and the initial policy probably does better than ImageNet pre-training. And also the grasping policy has features that are probably more suitable for grasping than ImageNet features. Okay, so qualitatively, we see that the pre-trained policy shown on the left struggles in situations such as harsh lighting, and it, for example, tries to grasp at its own shadow, while the fine-tuned policy is able to do much better. We also find that with transparent bottles, the initial policy trained on kind of more normal objects has a challenge of jamming at the objects and grasping at adjacent bottles, while the fine-tuned policy is able to grasp much more successfully. This is one of my favorite changes. So the offset gripper, the pre-trained policy has fairly bad aim with this offset gripper for understandable reasons, while the fine-tuned policy is able to do significantly better. And lastly, we also see significant gains in the checkerboard task, where it can also grasp much more effectively, where the pre-trained policy tries to grasp at the checker edges. Okay, so the takeaway from this part is that we can extrapolate to new environments with only an afternoon's worth of data. And some of our recent work has also shown, essentially by continuing to learn, and some of our previous and recent work has also shown that with meta-learning, we can accelerate the adaptation, the fine-tuning process, including on extrapolated situations. And we can also adapt a distribution shift with only unlabeled data, which makes this adaptation process even cheaper. So as takeaways for the entire talk, I talked about how if you want your agent to generalize broadly, you should try to train it on equally broad data by leveraging large and diverse data sets and building algorithms that can learn from them. I also talked about how we might try to figure out assumptions that will allow your algorithm to generalize much further. For example, assumptions about predictability, changes only being local, and assuming a modest amount of training data. And this can allow us to learn amidst non-stationarity and extrapolate to new situations. And with this general recipe, with these 2 points, I think we can get pretty far on the spectrum of generalization. With that, I'd like to thank my students. If you're interested in learning more about generalization, multitask learning, and meta learning, all the lecture videos from my course CS 330 are online. And I hope to take some questions later at the Q&A. Thank you.